Thank you. Hello, everyone. I am Aisha Al-Owais, presenting automation of meteor reduction using convolutional neural networks. To begin with, I am very happy to be here, happy to see names, familiar names whom we've been citing in our publications for the past few years. I'll take this opportunity to introduce you about the Sharjah Academy for Astronomy, Space Sciences and Technology. Then we'll move on to the introduction, followed by methodology, results, conclusion, and future work. So the Sharjah Academy for Astronomy, Space Sciences and Technology has several different labs in addition to a planetarium. And in this paper, we are presenting the collaboration between the Meteorite Center as well as the Space Artificial Intelligence Lab. In this picture, you see the building of the Academy, and here, this is an angle of the meteorite collection we have at the Academy. Now, coming to monitoring meteors, monitoring them is part of the Space Situational Awareness Program, and we need to know what is happening in the UAE sky. Also, there is a lack of archived meteor data in the MENA region, excluding data coming from Morocco and Saudi Arabia, as far as we know. So that is why we established the UAE Meteor Monitoring Network with the UAE Space Agency in September 2018. And as we can see here in the map, the network consists of 3 towers. One is located in Sharjah. This is in the Academy's premise. This is in a heavily light polluted area. The second tower is in Al-Yahar. The third one is in Liwa. And each tower is 5 meters high. Each is equipped with 17 cameras. It's a mixture of 6 and 8 lenses, as well as a fisheye lens. This is an example of one tower. This is the one in Sharjah. The other 2 are identical to this tower. The other 2 are located in the deep desert. Now, coming to the false alarm categories, we have 25% insects and airplanes, about 71% random light sources, as well as 4% camera noise, moonlight, and clouds. And the categories or the percentages of these types of noise, they differ from one station to another, depending on the light pollution in each area. So you can imagine the huge amount of data incoming from the Sharjah Tower, given that we are very close to the Sharjah International Airport. So we have a lot of airplanes captured by UFO capture, since that's the program that we use. Here's an example of what the false data looks like. Since UFO capture produces 5 different formats, we are presenting the masked version. These are just masked noise. Here's the moon, those are airplanes. And here's another example of noise that look kind of similar to meteors as understood by the CNN. And basically, this is what makes up our not meteors dataset. So to prepare our dataset, we utilized, this is a meteor, we utilized the masked version provided by UFO, and we converted them, whether it's a meteor or not meteor, to grayscale. This is easier for image classification. So it's either black or white. So it knows that if it's a white object, then this is the desired object that it will learn its edges and so on. This is what we do regarding pre-processing. To discuss the number of training images, we have data from the Sharjah Tower, which is with a lot of light pollution. The other one is from Al-Yahar, which is in the desert. So for the training images of meteors, we have about 7,000 for meteors and not meteors as well. And for Al-Yahar, we have about 4,500 for meteors and not meteors. And we also have some images close to 500 in Sharjah for validation, meteors and not meteors, the same for Al-Yahar images. Coming to the testing images, we tested the models on 1,200 meteor images, 4,000 not meteor images, and you can see the numbers here for Al-Yahar. Coming to the CNN models, first of all, this is the learning parameter, learning rate that we used. The epochs for the 4 models that we have, they vary. Some of them were trained on 20 epochs, the others were on 30 epochs. This was a result of a lot of trial and error after developing at least 20 models for each station. The optimizer we used was Adam, and the input size was 720 by 576 pixels, and this is where we vary from different proposed CNN projects in the Meteor area. So as a means to downsample the image, we kept it as is, but we introduced average and max pooling layers at the beginning of the architecture. And then it was followed by the conventional convolutional layer, followed by max pooling. And here we had batch normalization instead of ReLU, the rectified linear unit layer. The model progressed until we reached the end where we introduced the ReLU layer, followed by the dropout layer for overfitting purposes, finally fully connected layer and softmax layer to do the classification, either Meteor or not Meteor. The main difference between the Sharjah Meteor and Sharjah not Meteor is that here we used 20 epochs and here we used 30 epochs. Coming to the Yahar not Meteor model, it is similar to Sharjah, but it is less in terms of the needed layers. And coming to the Yahar Meteor model, the difference is that here we did not introduce average pooling layers at the beginning. And surprisingly, or maybe not surprisingly, it gave the best Meteor recall value, which we will see very soon. Coming to the automated reduction process. So we know that to have data of a full day, we need it from 12 a.m. to sunrise, and then the day comes in between. Then we need it from the sunset to 11:59 p.m. So we need to wait for a 24-hour cycle. So phase one occurs at 1 a.m. First of all, the folder is located. Then the program, a Python script, retrieves the date of the previous night. So it subtracts the day of today -1 to get the previous night. And then it extracts all of the masked version images, puts them in a temporary folder. Then all of those masked images get converted to grayscale. And finally, it is uploaded to an online repository. Why? Because the stations at the computer stations or the computers at the towers, they don't have the capability to run CNN models on them. That's why we have to upload them and download them in phase two. So phase number two, the folder is automatically downloaded. This happens at 3 a.m. Then the images are fed to the CNN. Finally, as an output of the CNN, we receive a list which has the names of the files which are suspected meteors. This list is then uploaded again to the online repository. At 5 a.m. On the computer that is within the tower, each tower, a folder with the data appended with the word reduced is created. So if we want reduced data of the previous day, we have the same date, but it's appended with the word reduced. It is also located exactly in the same place of the original file. Then the list of suspected meteors is downloaded. And then the program cross-checks the text file content with the original folder. So if there is an image in the original folder and it appears in the text file, then there is a match, meaning that this is a suspected meteor. What happens next is that all of those matching files or matching images, they get copied into the reduced folder. So when we come to work at 7:30 a.m., we don't have to manually go through the original file. The original file can contain thousands of files, but the reduced one contains much less. For example, yesterday's file of Al-Yahar contained about 1,300 images, but the reduced version contained about 240 files. Yes, there are false detections in the reduced folder, but at least no meteor has been missed so far. So this greatly reduces the time to filter out meteors. Now, coming to the results, we will look at the recall score for the Sharjah model. The recall score for meteors was 98, about 98%. For not meteors, it was 96. If we check the not meteor model, it had a better not meteor recall as 97.81%. So for Sharjah, because we have a lot of false alarms, we are more interested in choosing the model that is best at classifying not meteors. But for Al-Yahar, since noise is relatively less compared to Sharjah, it's not located in next to an airport, it's not located in a light polluted area. So we are more interested in the model which has a better recall score for identifying meteors. And we can see it here, 99% at scoring identifying meteorites compared to the other model. So for Al-Yahar, we choose this model, the Yahar Meteor model. And this is the architecture which did not have pooling layers at the very beginning. So in conclusion, the UAE MML compensates for the lack of daily meteoric events in the Gulf region. A thresholding method was added to the converted grayscale images, and this contributed to having a better data set because, for example, sometimes the whole image is colored in red because clouds are moving. So we put a condition that if the number of pixels exceed a certain number, then we neglect that image because it's most probably noise, not a meteor. The Sharjah models had better not meteor recoil, but the Yahar models had better meteor recoil, and we discussed the reason. And since during testing, we used 2 to 4 times more not meteor images than meteors in Sharjah, the Sharjah model resultantly had more accuracy. And because the images taken by the Yahar tower are less noisy, the Yahar meteor model was able to classify meteors more accurately. In addition, the images taken by the Sharjah are more noisy, thus the Sharjah models were able to classify not meteors more accurately. So the automation process of accessing incoming meteor data, reducing it, filtering out meteors, significantly reduced the need of an operator to manually filter the full and the original data coming from the towers. Considering future work, we will consider combining data from the 3 towers because we did not consider the 3rd tower in the study. So we'll do that to produce one model that would provide better meteor and not meteor classification accuracy. We might consider comparing the performance of CNN with hybrid deep learning models, such as CNN plus LSTM, CNN plus GRU, and not limited to that. We will also consider training the models using the full grayscale images instead of the masked images, just to compare the performance between the two. So this is in terms of developing the project in terms of convolutional neural networks. We do have a system that is trained on meteorites to distinguish between meteorites and terrestrial rocks, given that we have a data set at the academy. But our gap is in the triangulation and dark flight calculation. We don't have the expertise to have such calculations, so room is open for collaboration and knowledge exchange. And I believe that is it. This is what we have today. I hope you found this beneficial. It can be used for parties interested in reducing data coming from their stations. Thank you very much.